In this video, I want to discuss interpretations involving graphs for definite integrals. So here's a word problem that you might see. The birth rate, B of t, and the death rate, D of t, for a bacteria population are given in the graph below. So here's B of t is this blue curve, and D of t is this red curve. They represent the births at per hour and the deaths per hour for some bacteria population. And we're asked to find a definite integral that represents the total change in the population after 10 hours. So the key word here is total change. So when we're asked to find the total change in the population, what we want to do is find a definite integral. Okay, so in order to do that, we need to find the rate of change and then write that definite integral. What is the rate of change in the population? Well, there are two contributors to the rate of change. One is a positive contributor, which is the birth rate. So we have births, but then we have a negative contribution due to deaths. So the actual rate of change is the birth rate minus the death rate. And so we want to integrate that function, b of t minus d of t, over the 10 hours, because that's what we're told to do. And this represents the total change. Okay, so that's the answer to A. The second question is, when does the population reach a maximum? Now this has nothing to do with the definite integral. This is a problem that comes back from finding maxima for functions. So to find a maximum, we want to find critical points. And so for this particular function, the population function, where do we have critical points? Well, the rate of change in the population is given here. And so to have a critical point, it means that b of t minus d of t, the rate of change, should be 0. So a critical point will be given by b of t is equal to d of t. And there are two possibilities for that, this point and this point. Those are places where two functions agree. Now at this point, we're actually assuming that the population is 0, and after that point, the population increases because the birth rate is bigger than the death rate. So since the rate is positive, we're actually increasing. On the other hand, after this point, because the death rate is greater than the birth rate, we're actually decreasing. So here's where our maximum is. So that happens 6 hours after we begin watching this bacteria. Then the last part asks to write a definite integral that represents the maximum population. Well, certainly the total change in the population is up to the maximum is given by the integral from 0 to 6 of the rate of change in the population, which is b of t minus d of t. So that's the total change between when we started and we got to 6. Now we're going to assume that the population actually was 0 at time 0, in which case the total change actually represents the population. If, however, we had started with some other population, like we started with 100 bacteria at time equals 0, we'd have to add that 100 in because this only gives us the change from 0 to 6. Okay, that answers C. And now let's move on to another example. In this example, we look at the classic competition between the tortoise and the hare. And the velocity of the hare is given by the function h of t, and the velocity of the tortoise is given by the function t of t, and we've graphed these below. So here is t of t, h of t, velocity of the hare, and below here we have the graph of t of t. T of t is sort of the straight line function that starts at 5 miles per hour throughout the race, whereas the hare starts off fast at 20 miles per hour and then takes a siesta and stays asleep. It's this green curve. He's not moving at all until well after 40 minutes, makes 47 minutes, and he wakes up. Now, the first question asks, after 30 minutes, who leads the race? And to do that, we have to figure out how far they've traveled in those 30 minutes. So that's going to be the total change in their distance, and the velocity represents the rate of change in the distance. So we need to find the integral for, say, the hare. We find the integral between 0 and 30 of the hare's speed, dt. So that'll be how far he's traveled in first 30 minutes. Now, this is a pretty easy integral to do. In fact, you do it exactly because we have a rectangle, and then the area under the green curve here is 0. So the only contribution to that is going to be the area of this rectangle here. So that's going to be equal to 20, the height, times the base, which is 10, or 200. So that says that after 30 minutes, the hare has only traveled what he traveled in 10 minutes, which was 200. On the other hand, for the tortoise, he's traveling nice and steady all the way through the 30-minute mark at 5 miles per hour. And so his total change is given by 0 to 30, t of t dt, which is the area of this rectangle, which is going to be 30 times 5, which is equal to 150. Well, so what's the answer to A? Well, clearly the hare is still ahead after 30 minutes. He has gone 200, and the tortoise has only gone 150. So who leads the race? It's the hare. Now, write a definite integral represents how far the leader is ahead after 30 minutes. Well, we've actually written already 2 integrals, but we could form that into one. So it's basically 0 to 30, and I can write the hare minus the tortoise, because this is their relative speed. This is how far the change in the difference in the distances they've traveled. Okay, the last question asks, what time does the tortoise catch up to the hare? Okay, well, so far the hare only travels 200 in the first 10 minutes and then doesn't travel at all. So we just have to see if the tortoise can make it to 200 before the hare starts moving again. In fact, if you go up to 40, 40 times 5 is 200. So if we extend our rectangle to be to 40 minutes, then the total change from 0 to 40 is now the area under this rectangle, which is now 40 times 5, which is 200. The hare is still napping somewhere, and he's only gone 200 feet, and so this is where he's passed by the tortoise, this point. So at what time? At t equals 40 minutes. Okay.